Okay, so I'm gonna put, can everybody see my screen, by the way?
Yeah.
Yeah, okay. So I'm gonna put in the link. So there's, this project has kind of a technical component and then a more philosophical component. So I'm just gonna put in the chat here the link. The technical paper is already on the archive. If you want to see more details, go there. I'll be talking through kind of what we think is the philosophical significance of this. And let me say also, Jeremy's here. He's going to be correcting all of the mistakes that I make as we go, and I hope he'll be jumping in the discussion period as well, because really the bulk of this is Jeremy's work. Okay, so and okay, let's get started. So the question that we're interested in is, does classical mechanics, right, understood as this kind of higher level theory, reduce to quantum mechanics, which is maybe a more fundamental theory for us? One way to think about this question is to think of it as the question of, can we explain classical mechanics, classical phenomena, as well as the kind of theoretical structure of classical mechanics from the underlying theory of quantum mechanics. And we'll really, as we go forward, kind of be focusing on this explanatory question as opposed to, more questions about ontological fundamentality, for example. And our kind of primary foil here is Bob Batterman, or also James was mentioning Michael Berry, who Batterman has gotten a lot of these ideas from, or drawn on for a lot of these ideas. But I just want to quote Batterman here so we can get a sense of what attitude he takes towards the purported reduction of classical to quantum mechanics. So Bannerman says, it seems that most investigators maintain a reductionist and eliminativist attitude toward classical physics, given the many successes of the quantum theory. Of course, it's just this attitude that I've been at pains to question, given that the understanding of various observed and observable universal behaviors contained in the finer theories, that's quantum mechanics in this case, requires reference to structures present only in the coarser theories to which they are related by asymptotic limits. That would be classical mechanics. It is indeed difficult to see how this attitude can coherently be maintained. Okay, so his answer to this question of whether, oh, you guys can't see my slides here. Let me try this again. Okay, can you guys see my slides now? Are they in the right spot?
I see a screen that has Batterman on it.
This one?
Yeah.
Is it moving when I?
There's no movement.
Okay, I'm not sure why
it's moving. I can see your arrow now.
Okay, is that better?
It's not moving. That's what the question is.
Okay, I'm not sure why this is.
It's on the quote from Batterman.
It's fine. We can see the movement of your arrow now, but we can't see it, I think, when you go full screen.
It's moved now. It's moved now. It says Batterman. No.
Okay. Does anyone have a question? I mean, I can just keep it like this. It would be nice if we could put it full screen. Has anyone had this issue with Zoom before?
I don't think it matters if it's full screen. It's very readable.
Okay, good. Okay, so we'll just go ahead. So, okay, so here's the Batterman quote. It would have been nicer if it was up while I was reading it so you guys could get it. But this is Batterman giving, right, the main point is he's saying, no, classical mechanics does not reduce to quantum mechanics. And his reasoning here, right, so the summary is, he says, because the classical limit is singular in some sense. Either there's, you know, and it's in some ways, I think for us, hard to make sense of what exactly it means for a limit to be singular. But let's say it either means that we don't have convergence in an appropriate sense in the classical limit, or I think more generally, the point here is that Bannerman is saying that the structure of quantum physics on its own doesn't determine the structure of classical physics. That is, if you want to understand, if you want to explain certain classical behaviors, then you need information that comes from the classical theory and that's not present in the quantum theory alone. Okay, and so it's here that we want to push back. So I said, okay, so our claim generally, right, is that the answer to the title question is no, that the classical limit is not singular. But I've already admitted we don't really know what it means for a limit to be singular or not. And so what we want to say is at least it's not a singular limit in any way that prevents quantum mechanics from determining the structure of classical physics. There's no issue in getting the relevant kinds of explanations on the table here. So that's our central claim. And of course, there are going to be caveats as we go forward about exactly what kind of structure we're talking about, exactly what kind of explanations we're getting, and so on. And so I'll try to get to that as we go. The plan for the talk is, first, I want to do a little bit of setup. I want to talk about what it might mean to have a reduction here, and get some sense of what Batterman's problem is with the classical limit. Then we're going to talk about how to set up the classical limit in the right way, and we're going to present some results that we think guarantee the existence and uniqueness of the classical limit in a way that allows us to fulfill some existing reduction schemas. And then lastly, we're going to see that Batterman says, okay, even if you could fulfill some of the existing reduction schemas, he thinks that still wouldn't be enough for the structure of quantum physics to determine the structure of classical physics. And so we're going to try to say even more that there is a sense in which the structure of quantum mechanics determines the structure of classical mechanics as well. And let me say also, so if folks have clarifying questions or small questions as I'm going forward, I'm happy to stop and answer them. And I am keeping my eye on the participants list if you all want to use the raise hand feature. So just let me know. Okay, so let's just start off here by talking about reduction to begin with. So here's a famous and well-known schema for reduction going back to Nagel, and more recently kind of advocated for by Jeremy Butterfield. And so we're going to represent this schema with symbols in this way. So TB here is what we're going to think about as the bottom level theory. In our case, that's quantum mechanics. TT is the top level theory, the less fundamental theory, right? The higher level theory that's being explained. And D here is some collection of definitions or what Nagel called bridge laws. And so in order to have a Nagel-Butterfield style reduction, right, what you need is that there's some collection of definitions of classical terms from quantum terms, such that if you conjoin those definitions with the bottom level theory with quantum mechanics, that allows you to derive the top level theory, classical mechanics, right? Where these things, at least for Nagel and Butterfield, are often understood as collections of sentences in some formal language. Although we could detach the schema from that kind of logical thinking and just say, well, okay, there needs to be some sense in which the top level theory is derivable from the bottom level theory and some definitions of those top level concepts. Now, on the other hand, so there in physics, at least, we can often say more about this process of how we derive the top level theory from the bottom level theory. And so in physics, we often see that, this is formulated in terms of a limit. And so I'll just call this, right, a schema going back to Thomas Nichols. It's one that Batterman really deals with in his 2002 book. So the idea is that one way to make this derivation of the top level theory precise is to understand it as the limit of the bottom theory. If the bottom theory depends on some parameter epsilon, taking the limit as that parameter goes to 0. Okay, so in this case, right, TB and TT have the same meaning. TB is quantum mechanics, TT is classical mechanics. And so, the claim is that one other way to get a reduction of classical mechanics to quantum mechanics would be to show that the limit as some parameter goes to 0. And in this case, the parameter has to be Planck's constant. Well, I guess I shouldn't say it has to be. There are actually different kinds of ways of setting up relevant limits. The classical limit that we're going to consider is the limit where Planck's constant goes to 0. And in that limit, we ought to recover classical mechanics. Okay. Now, Batterman's claim is that if you take the limit as h bar goes to 0 of quantum mechanics, you don't get classical mechanics. So this is where he thinks things break down. So let me just give us some very quick sense of the argument or one of the arguments that Batterman gives here. So he says, look, one of the ways that we try to explain classical behavior is by using semi-classical approximations. And here's one of them, the WKB approximation. So imagine treating your wave functions in this approximation, right? In this form over here, the exponential of some function s over h bar. Now that h bar in the denominator of the exponential causes trouble because although these wave functions do allow you to reproduce some classical behavior in certain kinds of potentials, if you look at these wave functions and you try to take the limit as h bar goes to 0, you'll see that they don't converge. They oscillate wildly in that limit. Okay, and so Batterman says, well, we got some quantum states that don't converge to any classical state. And so the only way to really explain classical behavior, according to Batterman, is to treat these wave functions as asymptotic series expanded around the value h bar equals 0. And he said, okay, then we have to do some funny tricks, and we see that classical mechanics isn't really being reproduced by quantum mechanics here. Okay, so one fundamental problem here, not the only one, but one fundamental problem, according to Batterman, is that if you try to take the limit as h bar goes to 0, you don't get convergence. Okay, but we want to say the WKB method is just one method for taking the limit as h bar goes to 0, or just one method really for reproducing classical behavior. There are other methods, okay? So, and some of these other methods provide us with convergence. So if we take the limit as h bar goes to 0 in other mathematical frameworks, then it's possible we could get a reduction, right? Showing that one method doesn't work to reproduce classical behavior isn't the same thing, right? It doesn't allow you to conclude that there's no reduction in this case. And so here's a method where it's very clear that one has convergence in the limit as h bar goes to 0 in a precise sense. It's called strict deformation quantization. I'm going to have more to say about this as we go forward. And so what I want to move to now is introducing the methods that we want to use to take the classical limit, these methods of strict deformation.
Sorry, Ben, can I just say something very straightforward, clarificatory? Just if you go back, like, is Batterman's claim, like, is the claim that you can explain the same behavior using a different way of taking the limit, or that there's a different way of taking the limit, because it seems like the important point for Batterman is that you can't explain the same behavior. That Batterman's point only goes through if the other way of taking the limit doesn't give you the same explanation of the behavior or something like that. Do you understand what I'm?
Yeah. So, okay. So I'm not going to get into this in the talk, but let me say,
okay.
The behaviors that Batterman is focused on are, okay. So he has this argument about the WKB approximation. He has another kind of argument about chaotic behavior. The results about chaotic quantum systems that he points to, it gets a little bit subtle, because the claim that he makes is that one needs information from the classical theory in order to get certain results about chaotic systems. But our claim is that if one can reproduce the entire classical theory from the quantum theory, then one has enough, right? Then you have that classical structure. And so you can get, right, you can derive those
so in a sense, the idea is that you get the classical theory back in toto, and then you rederive the effects that way. So whether or not you can get all the behavior in one go isn't the point at hand.
Exactly. Yeah.
Great,
so
thanks. That's really helpful.
Yeah, we just want to get all the theoretical structure of classical mechanics. And I won't be able to spell out all the details here, but I'll at least gesture.
But I see the strategy of response isn't to say we can do anything you can do with this limit. It's to say that we can do everything with this limit, therefore we'll be able to get the explanation you want.
Exactly. And I'll flag here kind of as a caveat, there may be a substantive question. I mean, I don't think, I certainly don't, maybe Jeremy understands better, but I don't understand enough about these chaotic systems that Batterman points to. His claim is just that, if you had, the classical theory, you could get these results. And so all that we're showing is that you can get the classical theory. So as long as, what he says about getting those results makes sense, we say, okay, then we ought to be able to get that as well.
Thanks. Maybe we can talk about it more in the Q&A, but that was really good response to what I was worried about, but thanks.
Okay, good. Okay, so then let me move on now to explaining how we are understanding the classical limit and how we do understand it as reproducing the classical theory kind of in toto. Okay, so what's strict deformation quantization? This is the mathematical framework that we're going to use. It compares quantum mechanics and classical mechanics with the hbar goes to 0 limit. It can also be used for other kinds of limits. So it's actually a really nice tool. And a lot of our results are actually general enough to account for other kinds of limits as well. But the kind of unified mathematical framework that it uses to be able to compare quantum mechanics and classical mechanics is the framework of C-star algebras. Okay, so what's a C-star algebra? Here's my relatively friendly introduction. A C-star algebra is a collection of things where you can add them together. Okay, so you've got an operation of addition. You can multiply elements of a C-star algebra together. You can multiply them by scalars. The scalars are understood as complex numbers. Okay, that's my little c here. And then you've got two other operations which are maybe less familiar. You can take something, you've got something called an involution, which allows you to put a star above any element. This is going to be analogous to taking the complex conjugate, say, of a complex number. And then lastly, we have a norm on a C-star algebra, which essentially tells you about the maximum possible value that any element can take on. Okay, so a C-star algebra is just a collection of things that have these operations defined on them, and where these operations behave suitably nicely with respect to each other. And my claim is that we can describe at least aspects of both classical and quantum systems with C-star algebras. So let me give you two examples here to illustrate this. And let me say one more thing, which is that we'll think of the elements of a C-star algebra, these things that we're adding and multiplying together, as the physical quantities or maybe observable quantities in certain special cases associated with some physical system that we're interested in. Okay, so if, for example, we're analyzing a classical system, right, and the classical system has some state space or phase space, then a natural C-star algebra to associate with the system is the collection of functions on that state space or phase space. So if you give me, say the phase space of a system X here, and I'll say, well, the collection of continuous functions on that phase space, so assigning values, to each state, right? So each physical quantity we'll understand as assigning a value to each state in the classical theory. And there are some technical conditions that you can put on these functions if you want. You may ask that they vanish at infinity for certain technical reasons. But this is a collection of quantities that we can associate with the system. So for example, although this won't vanish at infinity, but if we're thinking just about continuous functions, the function that gives you the position in each state might be a physical quantity that you're interested in. The function that gives you the momentum in any state might be another continuous function that you're interested in. And then how do we think about these algebraic operations? Well, I'll say, if I want to multiply together two different physical quantities, I just multiply together their values on each state, pointwise. We'll call this pointwise multiplication. If I want to take this involution, this star operation of any physical quantity, well, that's the same thing as looking at all its values and taking the complex conjugate. And if I want to look at this norm, right, that's literally here looking at the maximum or supremum value that that function takes on. Okay, so in a classical theory, the collection of functions on phase space forms a C-star algebra. Similarly, right, in quantum theories, the collections of operators on a Hilbert space, the Hilbert space understood as the state space of the system, those form C-star algebras. So you could take either the collection of all bounded operators on a Hilbert space or some other sub-collection of those. You understand multiplication of operators to be composition. And in this case, multiplication turns out to be non-commutative. Okay, so whereas in the classical case, you've got commutative C-star algebras, and in the quantum case, you have non-commutative ones. The involution operation is taking the Hermitian adjoint of an operator. And then to understand the norm of an operator, you consider what's called the operator norm here. Okay, so classical and quantum theories both have collections of quantities that can be understood as C-star algebras. Okay, so now how do we use these things to take the classical limit? Well, suppose that you've got a classical system, you've got a phase space associated with it, and we're going to understand the collection of quantities on that classical phase space to be some algebra P. Okay, some collection of functions on that phase space. And this phase space usually comes with the structure at least of a Poisson bracket as well in order to formulate classical dynamics. Okay, a strict quantization. Okay, I'll usually omit the deformation part because we're not really concerned with this extra deformation condition. So sometimes it's called a strict quantization. But a strict quantization of the classical system that's represented by P is a family of C-star algebras. Okay, these are these AH bars, these fractor AH bars. One for each possible value of H bar in the interval between 0 and 1. Okay, so we've got a bunch of C-star algebras next to each other. And for each value of H bar, I have a quantization map, this QH bar, that maps from my classical quantities into the algebra at that value of H bar. And we require that if you look at any two quantities, then we have these three conditions that guarantee convergence of certain kinds of algebraic structures. Okay, so the first one, von Neumann's condition, says that if I take the quantization map and I act on A, and then I multiply that by the quantization of B, and I look at the difference between that and what I would get if I took the quantization of A times B, then the limit as h bar goes to 0 converges to the value 0. Okay, so that is that multiplication in the classical theory is close to multiplication in the quantum theory. Okay, the second one is Dirac's condition, which similarly says that the commutator in the quantum theory is close to the Poisson bracket in the classical theory as h bar goes to 0. And the last condition is a technical condition, the refill condition, which just says that we need each of that we need these quantization maps to essentially be appropriately continuous. Okay, so how am I supposed to visualize these things? Well, I've got a collection. Okay, so each of my circles here is one of these algebras at some value of h bar. Understand those to be the quantities associated with some physical theory. At h bar equals 0, my algebra A0 represents the classical theory. At all these other values of h bar, I have the collection of quantities associated with some quantum theory. And then I've got my quantization maps, right? That map us from the classical theory into the quantum theory and obey, right, that satisfy these convergence conditions. Okay, that's a relevant structure, right? These three approximation conditions give us a really strong sense in which the quantum theory converges to the classical theory as h bar goes to 0. Okay, and one thing I'll say that's different about this point of view than Batterman's is that we're focused on the observables or the quantities associated with systems rather than the states first and foremost. And that's where Batterman, sees kind of a lack of convergence, is because he's focused on very particular kinds of states in the WKB method. But if you move from that to thinking about the observables, then our claim is that you have a very strong sense of convergence. Now, okay, this will be helpful for us going forward. I actually want to move from thinking about these strict quantizations to thinking about a slightly different kind of structure here. So to motivate that, I'll say, look, we could have different quantization maps that might reproduce the same behavior in the classical limit. So I'll say that two quantization maps, Q and Q prime, are equivalent just in case they approach each other in the limit as h bar goes to 0. That is, if you take any physical quantity and look at what Q does to it, and then you look at what Q prime does to it, and take the limit as h bar goes to 0 of the difference, that's 0. In that case, right, if that holds for every physical quantity you could look at, then you would say that Q and Q prime are equivalent. Now, if you have equivalent quantizations, then you can look at the structure that's kind of invariant between these different quantizations. So the structure that these two quantizations that are equivalent have in common, and that's something that's called a bundle of C-star algebras. So it's really these bundles of C-star algebras that we're going to work with in the remainder of the talk. Okay, so here's a big long definition. It does fit on one page, but just barely. Let me mention some relevant features. So a bundle of C-star algebras is just like in a strict quantization. It's a family of C-star algebras, one for each value of h bar in the interval between 0 and 1. But then additionally, we have an extra C-star algebra, this fractor A more simply. That C-star algebra is something that we're going to think of as the collection of continuous sections of the bundle. Now then for each value of h bar, we have a map phi sub h bar, which we're going to think of as the evaluation map. Okay, and then there are some conditions that tell you that each of the sections in the C-star algebra A is appropriately continuous. Let me just skip those conditions though. We can come back to them if folks have questions, but I want to instead jump to a picture of this. Okay, so let me give you some terminology. So first of all, I want to think of the interval between 0 and 1 as the base space of a bundle. I want to think about each of the each of the algebras A sub h bar as a fiber over some particular value of h bar. And then I want to think of the algebra A without an h bar attached to it as a collection of cross sections of this bundle. Okay, so here's the picture, right? I've got now, I'm just going to explicitly put my interval between 0 and 1. That's my base space. At each value of h bar, I've got a fiber. That's one of these circles, okay, in algebra, a sub h bar. And then I've got another algebra of cross sections, right? These blue lines, maps, we could think of them as maps from values of h bar up to the fiber at that value of h bar. And these need to be appropriately continuous. So here, the only structure we've gotten rid of is the quantization map. We've essentially used that quantization map, or you can use that quantization map to generate a collection of sections here, but then you can forget about the quantization map that you started with. Okay, so we're just going to move to thinking about these bundles.
Can I ask a quick question? Is there any topological restriction on the fiber? Could it have weird structure, or does it have to be simply connected?
On the fiber algebra.
So I mean, in like fiber bundles in QFT, you can get these strange bundle, like topological kind of things in the bundle. Is this assumed to be simpler than that?
So the base space for our purposes, well, we just need the base space to be locally compact Hausdorff, and we will actually need it to be a metric space. For simplicity, right, I'm just saying we're really only going to deal in the talk with two possible base spaces: the closed interval between 0 and 1, and the half open interval, open on the 0 side. And so I'll mention that. Now, the fiber algebras could be any C-star algebra you'd like. So there are no topological restrictions there, except the ones that come from the C-star algebra axioms. Yeah. Yeah, good. And I mean, in some sense, the results that we're going to get are sufficiently general, right? That we just don't need those. Now, okay, look, here's what we want to say about these bundles. So we're not the only one who's used these to analyze the h-bar goes to 0 limit. Of course, we didn't come up with them. Klaus Landsman, in particular, has used strict quantizations to analyze convergence in the h-bar goes to 0 limit. And we think, you know, he's already done a great job here. And in some sense, our contribution is a very small one. But we want to point out exactly where it is. So we think, look, Landsman has done all this work, but there's a sense in which he doesn't respond to Batterman. And the reason is that these strict quantizations, or these continuous bundles of C-star algebras, they already contain all of the information about the classical theory in that algebra at A0. Okay, so here's my picture. You see that algebra A0, that's the classical theory. If you're understanding that to be part of the structure of the classical limit, then there's no way you can get an explanation of that. You've already posited it in the theory. So instead, what we want to do is ask the question, if we removed that classical algebra at h bar equals 0, could we recover it? If we started with only the information at h bar greater than 0, could we recover the classical theory? Okay, so here's our more precise version of the question. Given a bundle of C-star algebras over the half open interval, open on the 0 side, that is a bundle that doesn't contain information about the algebra A0, okay, that doesn't contain information about the classical theory, only information about the quantum theories for non-zero values of h bar. Can you extend that bundle to a bundle of C-star algebras over the closed interval? That is, can you extend it to one containing the classical theory at h bar equals 0? Okay, once we formulated this question, we get a precise answer. The answer is, if you give me any bundle of C-star algebras with the over the base space, that's the half open interval, open on the 0 side, then we can show that there is a bundle of C-star algebras over the closed interval between 0 and 1 that has the same fibers at every value and the same continuous sections, but adds in an algebra at h bar equals 0. Okay, so this can properly be understood as an extended bundle That is, if you give me all the information in the quantum theory, I can add to it a classical theory at h bar equals 0. And moreover, this extended bundle over the closed interval between 0 and 1 is unique up to a notion of isomorphism of bundles that one has to define. But there is a sense in which both the entire bundle over 0 and 1 is unique, and especially the fiber representing the classical theory at h bar equals 0 is unique up to star isomorphism of C star algebras. And I'll just mention here, the statement holds also whenever the base space, which here I'll call I, is a locally compact metric space. And if you can densely and isometrically embed it in another metric space, J, then I can extend a bundle over I to a bundle over J, and I can do it uniquely. Okay, but here we just need to think of I as the half open interval and J as the closed interval between 0 and 1. Okay. Let me mention here that also in proving these theorems, we get explicit definitions of all of the elements and the structure on the C star algebra representing the classical theory. So here's how it goes. You take this algebra A, that's the collection of sections of a continuous bundle of C star algebras, and you look at a certain ideal, that's this K0. This is the collection of sections that converge to 0 in the h bar equals 0 limit. And then you can define the algebra for the classical theory at h bar equals 0 in a relatively familiar algebraic way as the quotient of the algebra of sections by this ideal. And then the algebraic relations on the algebra at 0 are inherited from the algebra of sections. So, right, you can think about, well, I'll say here are the explicit definitions. If we're understanding elements of this quotient algebra to be equivalence classes of continuous sections, then you can define the algebraic relations on those equivalence classes directly from the algebraic relations on the continuous sections. The continuous sections here I'm denoting by little a and little b, and the elements of the C star algebra at 0 I'm denoting by capital A and capital B. Okay, so that is, we get a collection of explicit definitions, D, that we claim fits into the Nagel-Butterfield schema. So this is a sense in which here's D, right? You can plug that in, throw it in with quantum mechanics, and you get classical mechanics. And moreover, right, we claim that these conditions on a strict quantization show that there is a very strong sense of convergence in the h bar goes to 0 limit for the physical quantities of a quantum theory to the physical quantities of a classical theory. Okay, so at this point, what we have is that the h bar goes to 0 limit from these existence and uniqueness theorems and from these explicit definitions fits the existing reduction schemas. Okay, but now the question is that enough? Okay, so let's talk about this a little bit more. Are the reduction schemas that we get from Nagel and Butterfield or from Batterman and Nichols, are those enough? There's reason to think that they're not. And I just want to motivate that. I mean, this isn't our point. So I want to motivate this by going back to more things that Batterman has said. Okay, so of course, other people have read and responded to Batterman's work. Gordon Bellett in particular he's pointed out that, in some of the other examples that Batterman considers, in particular, in this example that Batterman uses about the correspondence between ray and wave optics. Okay, so where wave optics is a less fundamental theory, ray optics is the less fundamental theory being derived from wave optics. Bellett claims you can fulfill reduction schemas 1 and 2. But Batterman has a rejoinder to Bellot in print. So he says, look, if you're just giving purely mathematical definitions of the less fundamental theory, that's not going to be enough for a reduction. And the reason is that those definitions, although they may recover the less fundamental theory, may not engender the right kind of understanding of the classical theory. Okay, so let's just see what Batterman says here. So he says, although Bellot's pure mathematician could be given initial conditions and boundary conditions and be told to investigate the asymptotics of the relevant partial differential equation. Okay, so that's the relevant asymptotics from the more fundamental theory, which would get you to the less fundamental theory. But Batterman says those initial and boundary conditions are not devoid of physical content. So the information that you need to take one of these asymptotic limits isn't devoid of physical content. They're theory laden, and the theory required to characterize them as appropriate for the higher level phenomena in the first place is the less fundamental theory. Okay, I just took out, because he had put in, I think, ray optics and wave optics there. But I think the point stands more generally, even for, the classical and quantum case. So the theory required to characterize, according to Batterman, this particular, the information that goes into this limit as appropriate for classical phenomena in the first place is the classical theory. The so-called pure theory of partial differential equations is not only motivated by physical interpretation, but even more, one cannot begin to suggest the appropriate boundary conditions in a given problem without appeal to a physical interpretation. In this case and in others, such suggestions come from an idealized limiting older or emeritus theory. Okay, so like, how could we find our way around this objection? Well, let's just reformulate this question then. Okay, we need to think about the physical interpretation of these theories, not just their mathematical formulation. So the question is, does the physically interpreted mathematical structure of quantum mechanics determine the physically interpreted mathematical structure of classical mechanics? Now, we think that there's a way to answer this question as well, at least partially. And the idea is that we can actually encode at least some aspects of physical interpretation in the mathematical structure of a theory. Let me motivate this a little bit. So Neil Dewar has argued that interpreting physical theories involves at least two tasks. We're going to call those the internal and the external task. The internal task is answering this question: which mathematical structures in my theory are physically significant at all? The external question then is, what's the connection between those physically significant mathematical structures and the physical world? How do they actually represent things? But we could take these two things, somewhat separately, although of course they're related. And so we're going to focus on just these internal aspects of interpretation, because those, we claim, following Dewar, can be encoded mathematically using category theory. So what does category theory do for us? It allows us to focus on certain structure-preserving maps that preserve the physically significant structures in these mathematical formulations. So the kind of guiding principle here is that stipulating a collection of structure-preserving maps between mathematical objects is equivalent to stipulating the structures that are preserved, and to understanding those to be the significant structures that we're interested in. Okay, so that is, by stipulating a collection of structure-preserving maps, we can answer this internal question, right? We can say, oh, look, the structures preserved by these maps are the ones that are physically significant here. Okay, so slightly more formally here, slightly more precisely, what's a category? A category is a collection of objects and a collection of arrows or morphisms between them, where there are some conditions that allow us to appropriately compose arrows. Okay, so here's an example of a category. We've got some objects A, B, and C, and then some arrows between them. Here are some examples of categories, the only ones that we're going to need to use here. So we could think of C-star algebra, the category whose objects are C-star algebras and whose arrows between them are star homomorphisms, structure preserving maps between C-star algebras. And I'll say a little more about what the structure is that's preserved and why we think it's physically significant in both classical and quantum theories. But then we've also got a category of these objects that we use to formulate the H-bar goes to zero limit, a category of continuous bundles of C-star algebras. They're uniformly continuous in our case, so we'll call them U-bun C-star algebra. Okay, it's kind of a mouthful, so I may just call it U-bun. Okay, but U-bun is this category, and one can formulate an appropriate notion of structure preserving map between bundles, and we'll just call those morphisms of bundles. I won't put the definition up on the slides. Okay, so what are the physical structures in the category of C-star algebras? What's encoded by these structure preserving maps? Well, we've got these algebraic structures: addition, multiplication, the norm, the involution. Well, let me say, at least in the case where a C-star algebra is commutative, so at h bar equals 0, there's a result called the Gelfin representation theorem that tells us that this corresponds to the structure of what we're physically going to think of as a space of states or a phase space. So if you have a commutative C-star algebra, you can always understand it to be a collection of functions on what we're going to think of as a phase space. And moreover, that these structures specify the topology on that phase space. Okay, along with this, we get the possible values that each of these functions take on. So the possible values of each of these physical quantities, and so on. Okay, there may be some more structure that you want as well, but we get at least this. Okay, how about in the category of bundles, this U-bun category? Well, okay, mathematically, we get the same kinds of structures preserved, the algebraic structures on the collection of sections. But what do these correspond to physically? Well, first of all, at each value of h bar, so for each fiber, we get certain, if you've got quantum theories here, the multiplication relation tells us which quantities commute and which don't. And so they encode the uncertainty relations for the quantities at each value of h bar. Okay, and here, just focus on the values of h bar greater than 0. Moreover, these algebraic structures are sufficient to determine the spectrum of each physical quantity. What's the spectrum? That's the possible values that each physical quantity can take on. That's determined by the structure of these C-star algebras. And lastly, what we get in U-bun that's not present in a single fiber C-star algebra is an identification of how each physical quantity scales in different choices of units where h bar, Planck's constant, takes on different values. So I want to think about these different values of h bar, right? Whether it's 0.5 or 0.7 or 1 or whatever it is, I want to think of those as different values of the same thing, Planck's constant, in different systems of units. Okay, so if you change units, you get a different value of h bar, but it's understood as the same thing. Okay, but identifying that, and there's kind of a long story to tell here in a different paper. We'll just understand this to be information about how physical quantities change as you change your system of units. Okay, and we can, that's what's sufficient. That's all the structure you need to get the classical limit here. Okay, let me say a couple more things, and then I'll wrap up because we're kind of building up here. So we need one more thing, which is we need to be able to compare these different structures. And now the heuristic that we're going to use, is that if you have fewer structure preserving maps, fewer morphisms, that corresponds to more structure. And the reason is, right, that as you get more structure preserving maps, there's less that's preserved by them, and so there's less structure. But if you have fewer structure preserving maps, then there's a lot more that's preserved by all of them, and so that's more structure. Okay, so that's the heuristic we're going to use. And so what we need is a way to compare the number of morphisms in different categories. We need to be able to say this category has more morphisms than that one. Well, here's a way to do it. You use what's called a functor. And that's essentially a map between two categories. I'll just call them C and D here. It's really a pair of maps because you need to map each object from the category C to an object in D. Then you need to map morphisms from C to morphisms of D. But if you have a functor, then you have a sense in which the category D has more morphisms, or at least as many morphisms, more precisely, as C, because each morphism of C gets associated with a morphism of D. And so using the heuristic from the last slide, this corresponds to C having less structure than D. Okay, now our claim here, did I write that backwards actually? D has more morphisms, so that should be D has less structure than C, right? I think that's just a typo on the screen, as long as my brain's working this morning. Okay, so our claim is that there is a functor from U-Bun to C-star alg, okay? Actually, a collection of abelian C-star algebras, if we're focusing on strict quantizations, where this represents the classical limit of each bundle. So we've already got a construction that allows us to take the classical limit, right, and add in one of these fiber algebras at 0. That's what our existence and uniqueness theorems tell us. Moreover, our claim here is that if you take any morphism between bundles of C-star algebras, we can construct from that a morphism between the corresponding classical algebras. Okay, and you can define it in a kind of obvious way, but that I'm happy to talk through, but maybe in the interest of time, I'll just move forward. I do want to remark as well that if you start with a strict quantization, then the morphism that you get in the classical limit is also one that preserves the Poisson bracket. And so in some sense, it defines the classical structure of a Poisson bracket as well. Okay, so then the idea here, right, is that classical mechanics, if you understand it, right, as being partially interpreted, where the physically significant structures are encoded in some object, right, A0 in the category of C-star algebras, then that's got less structure than quantum mechanics if you understand it with a partial interpretation, where it's encoded in a bundle of C-star algebras in this category U-Bun. Okay, so in that case, by demonstrating that there's a functor here, we've shown, right, that classical mechanics has less structure, and its structure is moreover determined by the structure of quantum mechanics. Now, there's more that one can say here by actually looking at the properties that this functor has, but I'm going to skip over that in the interest of time as well. Just having a functor here, we think is already significant. Okay, so our claim here, I'll wrap up by saying our claim is that the physical structures of classical and quantum mechanics, respectively, can be encoded, right, using a partial internal interpretation. And that's by using the tools of category theory here. When so encoded, the structure of quantum mechanics determines the structure of classical mechanics, right? And that's this comparison that we've got, where we're able to say that the structure of classical mechanics has less structure than quantum mechanics. And lastly, because it's now been a few minutes since I said this before, I'll say, moreover, this relationship between quantum mechanics and classical mechanics, it does satisfy existing reduction schemas, both from Nagel and from Nichols. And now what we've shown is that on top of that, we think you can satisfy this additional desiderata that Batterman has for showing that the structure of classical mechanics is determined by the structure of quantum mechanics. Okay, so I'll stop there, and thanks all for coming, and I'm happy for the opportunity to discuss more with all of you.
Thanks so much for that. We'll take a 5-minute break and then start the Q&A at 5:35.
Great.
So I'll see you in
Oh, and students get to ask the first question. So students, think of questions.
Oh, sorry. Yeah, I should have said that. Sorry.
In fact, students have to think of questions, all of them. They have to be about the C-star algebras. I'm joking.
Yeah, or Stav, quickly email your question to a student.
I don't know. To be honest, James, with our students, I think they probably should email questions to me. I can pretend to ask them.
I'm just kidding.
Yeah, thanks, guys. That was really interesting.